box and public key encryption.
Yeah.
Take it away, man.
Okay, thanks for having me, and thanks for the introduction. And today we're excited to be here to talk about like white box learning and public key encryption. Joint work with Noam and Paul. So let me start with let me briefly recall the notion of public key encryption. So public key encryption, defines a set of like the algorithms defining like encryption, decryption, and like a distribution over public key and private key. So you think of it as key gen. And so in order for this to become like a public key encryption, we require correctness, which basically says, right, like decryption of the encryption should be equal to the same bit. So like encryption of a B under public key can be decrypted back to the same bit. And then we require security, which basically says that given the public key, encryption of 0 should be indistinguishable from encryption of 1 in the eyes of all efficient machines. Okay, so this is the crypto primitive we're going to look at today. And yeah, public key encryption is one of the central crypto primitives securing the internet, right? In the internet, if you want to visit a website, you need to do like handshake, and this involves like key exchange, which usually done using public key encryption. So so public key encryption is like a super important primitive, and what do we know about it? Like unlike private key primitives, only a handful of problems give rise to public key encryption. Okay, somebody told me like even private key primitives, there are not many problems from which we can construct. So yeah, so basically there are only like a few handful many problems from which we can construct public encryption, including number theoretic problems such as like factory discrete log, and we have like coding theory based problems, which is very close to like LPN. We have like lattice problems, and we have like noisy linear algebra based problems. So what do we know of about all those problems? If we look at those like number theoretic problems, they can be efficiently solved by quantum computers. So we basically have to kind of cross them off the list. If we look at coding theory, like noisy linear algebra based problems, lattice problems, they're all very similar. So like in a sense, they involve like solving like linear equations with noise. So today, the question we're going to ask today is, can we identify like a single assumption for building public key encryption that generalizes them all, or like a formula that's implied by all those like public key assumptions? Okay, so today our starting point is going to be let's start with LWE, and let me quickly recall like LWE. So LWE is like the problem of like learning with arrows. So it's LWE probably is like given like an instance where A is a like uniformly random matrix, you can think of it as like a tall and thin matrix. Okay, so if you have like any confusion, just stop me anytime. Okay, so if you look at the LWE instance A is like a uniform random matrix. It's it's like tall but thin, and we also have a secret vector X, which is usually like uniformly random, but we're not given X, we're given like A times X plus E. And if you look at the dimension, this whole thing is actually like a long column vector. So it looks very large, but it's actually like one vector. So you have first row of A times X, you get the first element plus some noise. And all arithmetic are done with like mod Q. So LW basically says that given such an instance, given like A and AX plus E, it's hard to recover to find back the secret vector X. If we don't have noise, it's easy. You just do like Gaussian elimination. So if this is overruled, I think this is called like a linear regression, which is also easy. So, but here we're adding noise, and we are in this like integer rings of modulo Q, which kind of makes this problem hard. And now let me expand a little bit where this name comes from. So why recovering X from this instance is called like a learning with arrows. So in a sense, we can think of it as like a learning problem, where we define our target function f sub x. We're trying to we're trying to learn like a target function, which is basically the inner product function with the secret vector x. And so we define the target function, like this x secret vector x is part of the description of the function, and we want to learn this like inner product function. And we can think of each row of A here is like a random example, like a random data point of my learning problem. And each row of this column, like AX plus E, this is a noisy label, right? So you get the inner product of the data points and my secret vector, and you pass like a little bit noise. So you basically can think of each row of this instance as like a sample of the learning problem, but the caveat is the label is like noise. And I guarantee you that the noise I add is like very small compared to the whole thing, so that you are still you still get like a lot of signal from like a noise sample. And the goal is to approximately compute this inner product function on like a freshly sampled like data point A. And maybe by approximately I mean like maybe you can compute this inner product function with like some certain level of noise, like even worse than the noise you get in the example. So therefore, we call it like learning with arrows. And note that here we are actually looking at the so-called like improper learning, where we're not we're happy with like any polynomial-size circuit that learns this target function, and so this is usually called like improper learning.
Why improper?
So I think like in standard learning problem, you want to find like a function from your hypothesis class that's kind of best explain all those data points. But here we don't care about the like we're happy with like any polynomial size. So if it's proper learning, you want to find like another. I know because here. So basically, the target function is like an inner product function, right? So to be like a proper learning, you want to come up with like an inner product that learns the actual inner product function, something like this. But here we're happy with somebody that's stronger, like any polynomial size circuit that learns this inner product. Okay, so let me mention that. If you're looking at the LWE, then you can actually turn, you can turn like an improper learner to like a proper learner by just recovering the secret vector X from like a polynomial size circuit that learns this inner product function. And basically, so if I have like a circuit computes approximately this inner product of secret vector X, how do I extract out the actual secret vector X from this polynomial size circuit? Well, suppose somebody can compute like the inner product function. So we actually figure out X like element by element. So first we want to compute say like X1, and the way you compute it, you take like a fresh LWE sample, you sample like a random column vector. And you add your random column vector, to the first column of A, and you use, like the polynomial size circuit that computes the inner product to compute, the inner product with like the first column with A, but add like a random vector in the first column. And you look at the inner product is like predicts, and you look at how many times your random vector here is added to this inner product. And then, if, so like this is still like noisy equation, but you can do like a brute force, you can try x is 1, x is 2, gives you, like an algorithm that runs in, size of the ring. But this is just, like a naive algorithm, and this like better algorithm that runs in, I think, like a log polynomials in log Q. Okay. So this is a learning with arrow problems. Now we're happy that this is a learning problem. let me explain that this is also a white box learning problem. Okay, so alternatively, we can think of A and AX plus E as the code of the sampler that allows you to sample like a fresh sample of this learning problem. So I take like A and AX plus E, I'm able to generate like a fresh like A prime and a fresh like a label for A prime but noise. And the idea is here, how do we generate this fresh A prime? We use, we follow the ideas in Gregor's PKE. We take like a binary, like a random binary linear combination of rows of A. So basically, you assign, like 0, 1, 0, 1, just random, like random binary linear combination of A, and you get, you just sum them, you just like sum them up, and you get A prime. And you use the same coefficient, you sum up AX plus E, you're going to get, like a noisy example, like a noisy label for this A prime. And note that why, so two questions. First, why summing up like an AX plus E gets you like a noise like some like the label, because each coefficient is either like 0 or 1. So even you add up all the noise in E, it doesn't blow up too much. So you think, like the noise is like polynomially smaller than everything else. So you get the good sample, maybe with like a little bit more noise, but I'm still good with it. And why this is a new sample, why A prime is a uniformly random like vector. So this you can think of A as like a randomness extractor, and extracting out your randomness in the binary random coefficients. And you can show, as long as you have like sufficient many entropy in the coefficients of the random binary combination, then you get like A prime that's statistically close to like a random vector. Okay, so here, like view it this way, we basically can get like a white box learning problem out of LWE. So basically, I can use A comma AX plus E to generate new samples myself. So think of this is the code of the sampler, which I can run, and I can get like a new sample of this problem. And the goal is still to learn this like a target function, which is still like an inner product function with my secret vector X. So therefore, we can like in LWE, we can actually, think of this as like a white box learning problem. And I think you can do similar things with LPN, but you don't get statistically close to random, but you get like computational close to some caveats. Okay, so any questions why this white box? It's white box because you get the code of the sampler and you can run the sampler yourself. And it's not like the Oracle there, like you get the Oracle samples. It's like you actually get the code. And in some senses, you just plug in a random tape to a sampler, you generate like a new sample.
So I mean, I guess maybe a couple things. Like, so I guess the sampler is like kind of limited. I mean, I guess you can't put in any random string.
Yeah, but you can think of, you can think of it as circuit, right? It's a circuit that takes like a random tape, and if you plug in any random tape, you get samples, and then you just put all those restrictions inside the circuit.
That makes sense. I guess noise becomes like a little bit bigger.
Yeah, a little bit bigger, but
maybe like you just thought you're like, oh, I can solve LW like a little bit bigger.
Yeah, I'm happy because still like I'm happy with like maybe a little bit larger noise. That's okay.
Yeah. Okay. I feel you.
Okay, and so today we're going to look at the white box learning problem in a more general form. So it generalizes this LWE from learning linear functions to learning polynomial-size circuits. And the caveat here is, we're not necessarily dealing with a uniform distribution. And it generalizes, the classic definition of pack learning from you get random samples from the oracle to having access to the code of the sampler. So this is a white box learning problem we're going to look at, like linear function to polynomial-size circuits, and compare with like track learning, like random samples to having the code of the sampler. Okay. So let me kind of briefly, introduce this white box learning problem we're going to look at. So we consider again like improper white box learning of where we're given the code, like a piece of code of the sampler for my learning problem, and this code samples me like a data point or example y together with like the label of y, but with like a little bit noise. So it's the sampler. I plug in a random tape to my sampler. It outputs like as example y and also like its noise label. And I guarantee that the target function f here is like p/polycomputable. It's like a polynomial-size circuit. And I also guarantee that the noise epsilon is more. And the goal is again, it's like a learning problem. So we're going to output like a polynomial-size circuit C that approximately computes the function f. So basically it says that we want to find like C such that the C of y prime is like close to f of y prime, where y prime is sampled from the same distribution defined by my sampler P.
So why p/poly? Like, does p not enough? Are you getting something from the
Here we're kind of looking at like we're looking at learning circuits. So yeah, because doesn't make much sense if you learn a bunch of constant like thing of constant size. Yeah, so it's kind of more reasonable like you're looking at circuits and you're learning polynomial-size circuits. Okay, maybe a couple of questions would be, like the sampler, we need to be careful about the sampler. So they maybe, my point is like maybe there's some other way of learning, right? Like maybe the sampler just leaks the function f. And maybe you can just, read the code of the sampler, then you obtain the function f. Or maybe the sampler leaks, like partial information of f. So I mean, like given the code of the sampler, I give you like potentially more information, and maybe this potentially makes the learning problem easier. But it's like non-trivial because from the LWE example, there's a clever way of constructing the sampler P such that even you read the code of P, it doesn't leak very much about the target function you want to learn. Okay, questions? Good. So today we're going to show, like a worst case hardness of this white box learning problem when we restrict it to like a notion of natural strings, like natural instances, like the worst case of hardness of white box learning restricted only on like natural instances or characterize the existence of public key encryption. And in order to obtain PKE, we're going to, let me explain what does like natural instance mean. We're going to look at, the code. So basically the code of the sampler P and together with the target function F such that they have like a so-called small computational depth, where computational depth is, like it's a kind of a notion from Kolmogorov complexity literature. And let me highlight that, here the code is basically like a binary string. And the function f, we're thinking of also like a binary string. So it's basically the depth of like a string rather than depth of circuit.
So this is just like, this is the problem we look at. We'll only look at.
Yeah, only if the code is like, does not satisfy my property, I don't care about that instance. I only care about, all those like instances such that their computational depth is.
So why does LWE have small computational depth?
We're going to explain very soon that, basically nature strings will have small computational depth. And I will define like many of the nature like second. So let me kind of briefly explain, the notion of Kolmogorov complexity and what is computational depth. So Kolmogorov complexity basically is like a measure of amount of randomness in a fixed individual string. So we define for any string x, we define k of x to be the quantity of the length of the shortest program that outputs the string x. And usually, if a string is like a random, then it's going to have high Kolmogorov complexity because there's no short program outputting this string. And you can think of the second string seems very random, and the first string, right? You can have like a short program generating the first string. So the first string has like small complexity, so it's like not very random. And we can define the time bounded variance of this Kolmogorov complexity. So here we fix like a runtime bound t. Think of t as like a polynomial or like n squared, and we restrict our attention to programs that efficient programs or like programs that will terminate after t of length of x step or like a length of x squared steps. So this is the notion of Kolmogorov complexity and this time bounded variance. And they are all proposed by Kolmogorov in the 1960s. And here is the example of the first string, the Python program. Here we can think of all the programs as like Python programs. And you also see like a beautiful image here. If you're curious about it, it also has like very small description. It's actually like the x squared plus c function. Okay, so the Kolmogorov complexity has lots of connections like between Kolmogorov complexity and cryptography. And let me kind of explain the notion of computational depth that we rely on. So the computational depth is defined to be, for any string x, it's defined to be the kt complexity of x minus the k complexity of x. So it kind of says that, how much you can compress more if your algorithm is like time unbounded. So kt of x is, the smallest compression with, the generation algorithm with the decompression algorithm is like efficient. But the k of x is basically, the smallest compression where the generation algorithm can be decompression algorithm can be time unbounded. So the computational depth basically says, how much more x can be compressed if you allow like time unbounded algorithms. And we can define, say as superscript t to be, all the strings such that you cannot compress by too much. Like you can only compress by say like 10 log n if you're time unbounded. And we call this the CS, that is, that of all computational shallow string. And this is going to be, like the restriction we're going to add in our white box learning problem. And
yeah. So what's an example of a string that can be compressed a lot? Like a string that has very high computational depth?
Good point. We don't. So again, it was a question like the string can be compressed a lot, but the computational depth is also high.
Oh, let's just start with the string that has high computational depth.
Yeah, they are rare. So we really don't know. So maybe let's start with think about like a random strings, right?
Yeah.
If I have like a uniformly random string, then like the time unbounded algorithm is not going to be not going to do like a lot better than just the naive compression, which is like print the string. So basically, time bounded version is like roughly n, and even if you allow like algorithm to be time unbounded, it's not going to be improved like by a lot.
Maybe I have an idea. Maybe if you set t to be like, I don't know, like if you set it to be like quadratic or something, and then you say, okay, output like the first like n primes or something, then well, there's this very short program that can output the first prime that just like is very expensive to find, right? So I guess like
can you say that again? Like,
yeah, I don't know. Maybe it's not super relevant.
Okay, so
yeah.
So the point here is that computational shallow strings are kind of rare and hard to find. Like why? Because this is so-called slow growth like law. So basically says that given like any like a, efficient randomized algorithm or like a sampler that's outputting strings, then the probability that M outputs something outside the computational shallow set is going to be tiny. It's going to be 1 over the probability that M outputs something outside this set is going to be 1 over n to the 5, smaller than 1 over n to the 5. So basically, this is that given like any efficient sampler randomized algorithm output string with very high probability, with like 1 minus 1 over n to the 5 probability, you're going to land in my computational shallow set. And the caveat here is the running time of this algorithm is this t prime needs to be smaller than the runtime bound t in my time bounded Kolmogorov complexity. So basically, if you look at t to be, actually, like the runtime here doesn't really matter here because we can, okay, maybe say like t equals like n to the 10, then, adding n to the 5 time algorithm will not find, any string outside the computational shallow set with high probability. So this is kind of why we call it like, set of natural strings, because if you look at the uniform random distribution, then it's always going to be computational shallow. And if you look at the other extreme, like if you have like a deterministic algorithm outputting like a single string, like always, then this string will for sure have very small time unbounded Kolmogorov complexity, but it also has like small time bounded Kolmogorov complexity because it's generated by like a fixed deterministic algorithm. Okay, so like arguably computational shallowness is like a measure of naturality. Most strings are going to be computational shallow, and to find a non-shallow string, you essentially have to pay more running time than my running time bound into like a Kolmogorov complexity. And this notion of computational shallowness has like a lot of applications, like average case complexity, cryptography, and meta complexity. Okay, so today we're kind of going to look at only instances in this set. And if you're, like you're not unhappy, you're unhappy with it, just think of, any kind of time-bounded sampler. You can think of this as an average case notion that's, like where my sampler can be, like an arbitrary distribution that's like time-bounded. Okay, so let me kind of quickly define, like a bit formally the notion of white box learning problem. And here, like this white box learning problem, we're given the code of the sampler P, or think of P as like a circuit, and I'm given the description of the circuit. And you can sample like a instance of the sample of the learning problem, like X and Y, using this sampler. And let me define this, complement circuit to my distribution. So basically, this comp set is a set of circuits that can expand my distribution. And I have like 2 parameters here. The first is like a delta, basically says that how much noise I tolerate. And the second parameter is the epsilon, which basically says how good the circuits are. So given delta and epsilon, this comp set of the distribution P is like all the circuits. And here I'm also thinking of circuits with a description, such that with high probability, with like 1 minus epsilon probability, the output of the function of the circuit of the function f is close to like the label that generates my distribution y, and like with high probability they're going to be close, and the close it's like within like a delta distance. So here we're really looking at integers rather than this length means really think of it as like integers rather than like timing distance. And the probability is taken over, like this distribution of my sample. Okay, so the input of the learning problem is defined by the description of the circuits of the sampler, and I guarantee you that there is like a good circuit. So there is a circuit with tiny tiny arrows like a delta divided by n to the 10th, and it's going to be always correct, like with like 1 minus 1 over n to the 10 probability correct. So I guarantee give you a description of the sampler. I guarantee you there's a very good circuit that extends, that's consistent with the sampler. And the goal is to just find something, like something okay circuit, maybe like with like a little bit large noise, and maybe the success probability of the circuit is like 2/3. It's not as high as the one that I guarantee to exist.
So wait. So first of all, what distance are you working over? Is it any distance?
I know. Think of this as all like integers. This is really absolute value of the two things.
Okay. So maybe you can tell us how LWE fits in this variable? Like LWE is one of those things, right?
Yeah, LWE is like you use your like a comma ax plus e as the code of the sampler p, right? And then it kind of defines a distribution where this x is uniformly random and y is just like a noise version of the inner product with a data point with a secret vector. Yeah, and I guarantee you this like very good circuit is basically the secret vector. If you know the secret vector, you can do this like very well. And we're looking for something that's maybe with a little bit more noise, and maybe it's like not always succeed. So yeah, so given like we guarantee that like very good circuit exists, then we just need to find like an okay circuit. Okay, now we are going to add our restrictions. Basically, it says that we're going to only look at instances that from this computational shallowness restriction. So I'm going to only look at the code of sampler P and the circuit C prime. Yeah, so I'm going only look at the sampler code of sampler P and the circuit C prime such that they are kind of computational shallow. Or like so basically we only look at white box learning restricted like natural instances. And so the hardness assumption we're going to need is this like white box learning restricted to computational shallow instances is not in this like IO FBPP, which basically means that for any PPT like learner, or PPT algorithm, it fails to learn some computational shallow or like some. So I have like set of all computational shallow strings, and for every point time learner, it fails on some of the instance in the set of computational shallow strings. So this is going to be the hardness assumption we rely on. So any arbitrary like a learner, polynomial time learner, it fails to learn some instances in my set. That's a hardness assumption. This stands for like infinitely open function PPP. Yeah, it's a kind of search problem, and infinitely open you need like almost every hardness problem. So that's kind of explain our main results. So we're basically saying if we fix some like error parameters, it's kind of okay, and we consider any polynomial running time bound T, then the following is equivalent. So the worst case hardness of white box learning restricted to natural instances is equivalent to the existence of public encryption. And therefore, hardness of this white box learning on natural instances characterizes the existence of public encryption. Okay, so then let's, like maybe here we're learning like polynomial-size circuits. Let's, maybe how about we look at maybe some like a weak class of functions. So we kind of instead we can consider the task of learning like polynomials with the bounded degree. So here we're kind of introducing like a new like parameter, which is the degree of the kind of the target function we want to learn. And then we just consider, like the target function instead of a polynomial size circuit, we think of it as like a degree polynomial over like integer rings of modular Q. Okay, so like any polynomial size circuit, you can be written as like a polynomial with like a polynomial degree, and then we can show that using kind of complexity leveraging or using like padding arguments, you can show that like public key encryption equivalent to learning like functions, polynomials of polynomial degree or polynomials of like n to the epsilon degree. So this is essentially you kind of, you take an instance, but you run like doing like complexity leveraging, you use, the first of the first couple of bits to do to define this learning problem. And so, okay, then you can think of, LWE is super close to, learning like linear functions. So basically, we can show, assuming LWE implies like hardness of whitebox learning like a linear function. And this is idea we kind of sketched in the very beginning. This is just use like a regular PKE as explained before. And what's interesting here is you might, maybe actually maybe the converse direction is also true. Like namely, if this is hard, this implies the hardness of LWE. Like why? The intuition that suppose we want to show, the converse direction. We want to show that hardness of whitebox learning also implies hardness of LWE. If it's true, then this is the equivalence. And the intuition here is assume there's, LWE is easy, and then we have worst case to average case reduction for LWE, and therefore we should be able to break LWE on any instances. And then this is sufficient for us to break this whitebox learning problem. And so seems to be true, but I don't really know. If you are lattice experts, happy to discuss this. So the converse is not, we don't know. Like, so the caveat here is kind of the worst case algorithm we obtained from the lattice reduction is called like bounded distance decoding. It only works when the lattice instance you define has shortest vector longer compared with noise. So it's worst case hard. So this worst case algorithm we obtained from the lattice problem is like a promise, like a algorithm for a promise problem, where the promise is the shortest vector in the lattice is long compared with noise. And if you have like a uniformly random like matrix A, and then you can show this happens with like very high probability. But if it's just like an arbitrary instance of matrix, then we don't really have this guarantee. So then this whitebox learning problem is like seemingly weaker, even if we restrict it to like linear functions.
So maybe like a question, maybe you were going to talk about this, maybe you actually didn't, but like I guess two pretty clear examples of problems in this class are LPN.
Yeah.
Like, are there other examples that we can conjecture are in this class? Like,
good point. Like you can think of it as like a general problem where you get like a circuit, like a circuit that defines the distribution of learning problem with a promise that there's a target function that's consistent with the distribution.
Yeah.
And just look at all those like circuit descriptions such that they are kind of natural. Or
it just seems really hard. Like I feel like when I think about like what's kind of really special, other than like other kinds of structure which are useful, when I think about what's special about LWE and LPN is that you get the code to the sampler, but still figuring out what the real hidden circuit is hard, right? Because usually if you get the code of the sampler, like for most problems, like you got the code. So even if
not necessarily, right?
Well, maybe.
Yeah, it's kind of like a new perspective looking at learning problems, right? So usually we're just getting samples, But what if I'm also having whiteboard access to the code of the sample? And does it makes it, is it still hard sometimes? Okay, so let me mention that there's a kind of standard degree reduction techniques where you can bring down from any constant degree to degree 1 to like learning linear functions. So kind of the idea behind this is, if you want to learn like a degree, like a polynomial of constant degree, then you can construct like a new function where you can like pull out all this like a monomial in your polynomial, and you can make like a linear function out of all this like monomials, and then this is going to be like a new instance of learning functions, learning linear functions. So the standard degree reduction that works from any, for instance, degree of any constant to degree 1, and would be interesting, to see anything we can do if we have like a logarithmic degree. Can we show that such a degree reduction can be, dropped down to like linear functions?
What's this subscript P mean?
Oh, this means kind of a reduction. Yeah, this means this is like you can take like a learning constant degree function and transform it into an instance as learning like a linear function.
You mean like polynomial time reduction?
Yes. Okay, finally, I want to talk about the relationship between black box learning and one-way functions. So basically, if we can classical results, we know from classical results, we know average case hardness of pack learning is equivalent to the existence of one-way functions. And this is basically, a worst case analog of those classical results. So yeah, basically says that if you have. Okay, so maybe let me quickly sketch kind of how we prove this equivalence, and maybe let me start with the first direction, where we assume that there's some white box learning instance that is nature, and we assume any polynomial time learner fails on some certain natural white box learning instance. Then we want to construct like the PK public encryption. Okay, so in order to make my life easier, we assume there's no noise. So the sampler defines like learning problem with no noise, and we want to learn it also with no noise. And we consider, say, like a runtime bound to be like n. And it suffices for us to first construct the so-called like a weak public encryption. Weak public encryption basis is that it doesn't have perfect correctness, but it has correctness with probability 1 minus epsilon. And for security, we just ask like a weak security. So like no adversary Eve can predict the message given the encryption with probability slightly smaller than like 1 minus epsilon. Here maybe like 1 minus 20 epsilon. And we can use standard like public key encryption amplification to amplify such weak public encryption to PK. Okay, so let me quickly sketch kind of the PKE construction. So here, so I'm going to, so first step is, I start with hardness of white box learning problem. So the first step is to sample like a pair of like a learning problem. So like a sampler P and also like a target function C. And how do we sample it? So here we're basically taking random programs. And we're picking like a random programs of random length, and we just run this program for a certain number of steps. And we simply interpret the output of the program as like the code of the sampler and the target distribution. So if you don't like sampling like random programs, think of this as there exists like a distribution over over the code of the sampler P and the target function C. I can think of, maybe there exists a distribution over this. And of course, because we're starting with, like a random programs, so like the description of the sampler maybe is like inconsistent with the target function C. So basically we have to like manually check whether they're consistent. And this check, we just, just take random samples from P and we just test whether it's consistent with the circuit. And if this test passes, we just set the public key to be the white box instance that we want to learn. And we'll set the secret key to be, the target function behind it. Okay. So this is public key construction. First, we sample like a P and C. Here we're kind of doing this so-called like a universal distribution. If you don't like, so here we just sample like a random program of random length, and we interpret the output as like description of sampler and target function. If you don't like this, you can think of there exists a distribution over the thing. And second step, we need to like checking consistencies. Basically, we take like random samples from the sampler and we check whether it's consistent with the target function C. And if the check passes, we set the public key to be the white box learning instance we want to learn, and secret key to be the target function. And encryption, decryption is also kind of straightforward. So in order to encrypt like a bit B, we just take like a sample from the sampler P. Consists of like a data point, example X, and also like a label for its Y. And because we're the hardness of learning P basically says that even I give X, it's hard to find Y. And this is where we can use it to like encrypt the message. So we're going to encrypt the message B by outputting X together with the so-called like gold-like 11 one-time pass of the label Y. So basically we're given out like the data point X, and we'll use the real label of X, Y to encrypt the target B. So basically sample random vector R and do like a so basically compute the gold-like 11 bits of Y. And to decrypt, so because the secret key is the actual like the target function, so you can compute the label using the target function, and you use this label to compute the gold-like 11 bits, and then you can decrypt. So this is the encryption and decryption. And we can say correctness basically follows from the construction, because if P and C is like inconsistent, then it will be caught with high probability during my consistent check step. And so to show that it's secure, so we basically want to say that if there's an adversary if that can predict the message B given the encryption, then we're just going to use the adversary to construct the so-called like white box learning. And I'm not going to go into details of this. So basically, the idea is like if somebody predicts like the message from the gold-like 11 like encrypted encryption, then it's actually you can actually predict the gold-like 11 bits, and you can transform that into an attacker that will recover the whole label Y. And if you can, given the data point X, you can recover the label Y with very high probability, then this is going to be like a white box learner for the instance. Okay, so going very fast here, like I'm not dealing with the worst case, why this works in worst case, but some technicality to deal with the restriction on natural instances, but this is kind of roughly the idea. Good. And so let me quickly sketch like the other direction. So in the other direction, we want to show that the existence of public encryption implies the white box learning problem is hard. And then, so the goal here is to construct the white box learning like instance from public encryption. And here, the white box learning instance is basically we generate like this data point or like the example is just the encryption of a random message. And the label is basically the message itself. And you can do this using the public key. So you're going to release, like the public key in your white box learning like instance, and you're just using the public key to create the new samples. And the target function of this is basically the decryption function. So which has, like the secret key defined by the secret key. So it's like polynomial-size circuits. And if we're able to like learn this white box learning instance, so basically breaking the semantic security of public encryption. And next, we need to argue, why those instances lie in this computational shallow set. So basically, this is an expense, right? So this keygen is like a randomized algorithm outputting strings, and any such algorithm will output strings in this computational shallow set with very high probability. But there are some caveats in order to prove this, because this computational shallowness holds only under de-randomization assumption, but we have a way to prove, the same statements without de-randomization assumption, and that's like it's like a little bit technical, and I'm not going to talk about it. Okay, questions?
Yeah, I mean, so maybe just trying to kind of wrap my head around like the abstraction and see where does it bring us with like big problems I'm familiar with. Is there like a direct way to see why something like DPH or like discrete log, right, which imply public key?
And yeah, and then you can
related
define, like a white box learning problem where the white box, like the code of the sampler has the public key of your encryption hard-coded.
Yeah.
Say,
sorry.
Okay. If you have you have like G to the X hard-coded in the instance, right? And then this is outputting like G to the XY comma Y, right? And then the solution. So in the solution, you just have like the secret X in your target function, which you can kind of which is like a polynomial-size circuit.
But it's not the case that like DPH or something like that is an instance of WB learn. It's not. How would you sample like new instances from the DPH?
No, you can basically define, like a learning problem with respect to your DPH instance, right? Yeah, kind of in the same way, like how you plan your public key in the code of sampler, then you can sample from like encryption with message, and the goal is to kind of learn the message.
Okay. Okay.
Okay, so this is kind of idea. So let me kind of quickly wrap up. And today we have seen that, like a white box learning restricted to computational shallow instances equivalent to PKE. And we also kind of see, like by how much this task of like problem of LWE overshoots the task of PKE. So basically, if we can show like a hardness of learning polynomial circuits implies hardness of learning linear functions, then we show like LWE is kind of equivalent to public encryption. And also showing when functions implies PKE is equivalent to showing that you can get like a white box learning instance from like a black box learning instance. And let me end with like interesting open problems. So the question here is, can we obtain like efficacy from this white box learning framework? Because say we look at white box learning of like a linear function, and maybe you can construct like FHE using the same paradigm, we construct like FHE from LWE. And the caveat here is we don't have an amplification theorem for FHE, or like a combiner for FHE. So here, recall that we didn't really get, like we get only a weak public encryption from this white box learning problem. And if you want to amplify weak schemes to strong schemes, usually what you do is like, you have a message, you kind of secret sharing it, like you kind of add redundance to your message, and you encrypt each like share with like a fresh, like a random fresh like encryption. And as long as you do this, you put your message in this like a linear secret sharing, and we don't know how to get FHE. We kind of lose like a fully homomorphism after you do it's like a linear secret sharing. And the actual amplification theorem could be even worse. It's not so in the actual application we're not doing like a linear secret sharing. It's something non-linear. And so this is open question 1. Can we get something FHE? And open question 2 is can we kind of close the gap between public encryption and LWE? So now we can reduce constant degree to like a degree, like we can reduce constant degree to degree 1. And the question is, can we reduce maybe from like polynomial, like a logarithmic degree to constant degree? That's even just that is thing like
reduce what? Like you mean like if I have like a XOR instance for K being log n, can I solve?
No, if you have no, like if so, you start with a learning problem where the target function you want to learn is a degree log n polynomial, and can you show that that can be reduced to like a learning problem of degree constant?
Why would we have hope for that being true?
We don't know. Like
okay,
we have we can reduce like constant to 1, right? And maybe if you do something smarter, maybe like you can reduce log n or even like a log n to constant.
But, yeah, the blow up I guess is like you're using linearization. So the blow up in instance size.
Yeah, it's going to be like 2 to the degree. So the naive approach just doesn't work. Yeah. Finally, can we somehow can we have like can we relate black box learning to white box learning? And it would be interesting even because here we only know how to do this from LWE over like a uniform distribution. And the interesting question would be, suppose it's a not uniform distribution, can we do the same like a rig-up trick, over the distributions that are not necessarily uniform? Okay, that concludes my talk. Thank you very much.
Thank you.
So I guess maybe question.